Good day viewers, welcome back to my channel. Today we're having the following MIT integration B problem. Integral from 0 to pi all over 2, the cube root of tan function of x all over sine x plus cos x in bracket squared dx. How do we solve this problem? Please, if today is the first day of visiting my channel, please subscribe to this channel to help the channel grow. How do we solve this problem? At first glance, I believe this problem looks monstrous, but not hard the way we think. Okay, let's see what we're going to do. We'll be using the following properties to solve this problem. So we have the sine tan inverse of x is equal to x all over the square root of 1 plus x squared. Cos tan inverse of s is equal to 1 all over the square root of 1 plus x squared. Okay, then over to this particular special function, the beta of mn is equal to integral from 0 to infinity x raised by n minus 1 all over 1 plus x raised by n plus n dx. The beta of mn, the relation, that is the relationship between the beta function and the gamma function. This is equal to gamma of m times gamma of n all over gamma of m plus n. And here we have the Euler reflection property here. The gamma of m times the gamma of 1 minus m is equal to pi all over sine pi m, given that 0 is less than m and m is less than 1. Here we have gamma of m plus 1, which is equal to m times gamma of m. I believe this makes sense, right? Okay, now let's go back to our problem. Here I'll be making the following substitution. So I can select tan x equals y. Okay, so here x is equal to the tan inverse of y. Differentiating both sides, so we get a dx is equal to dy all over 1 plus y raised by 2. Okay, now our integral will become integral. So here let's check the new limits. Now if you put x equals 0 here, so we get y is equal to tan of 0, which is 0. When you put x equals pi all over 2, we get y is equal to tan pi all over 2, which is infinity. So y is going from 0 to infinity. So here we have cube root of y all over open bracket. Remember what I said? The identities I showed here. Sine of tan inverse of y is going to be y all over the square root of 1 plus y raised by 2, then plus cos of tan inverse of y. Remember s is equal to tan inverse of y, so this is going to be 1 all over the square root of 1 plus y raised by 2, then everything squared. And here we have the s. The s is equal to dy all over 1 plus y raised by 2. Okay, let's put a multiplication sign here. Now from here, this is equal to integral from 0 to infinity, cube root of y all over. Here we have common denominator, so in the bracket we have y plus 1 all over the square root of y 1 plus y raised by 2, then squared, times the y all over 1 plus y raised by 2. And here we have integral from 0 to infinity, okay, cube root of y all over cube root of y all over. Remember, we're going to make use of this following indices law, that a all over b raised by n is the same as a raised by n all over b raised by n. Okay, so here we'll be having y plus 1 squared all over square root of 1 plus y squared. So we are just left with 1 plus y squared. Then remember we have times dy all over 1 plus y raised by 2. Okay, so simplifying this, we have integral from 0 to infinity cube root of y all over. So we have here cube root of y all over here 1 plus y squared. Take this inside, so we have here 1 plus y squared everything all over 1 plus y squared, and here we have dy. So this and this gets cancelled out. Okay, so now we have this to be equal to integral from 0 to infinity. So we have cube root of y all over 1 plus y raised to 2 dy. Okay, so from here we're going to make use of the beta function. Okay, so like I showed earlier, so this is the property of the beta function. So integral from 0 to infinity x raised to n minus 1 all over 1 plus x raised to n plus n dx. Okay, so let's try and make that integral to look exactly like this when we have a number subtracting 1 from it and the same number and another number which we sum to give the power of that 1 plus x. Okay, before we take the special function. So here I'm going to rewrite as follows. So this is equal to integral from 0 to infinity. Remember, y cubed means y raised to 1 all over 3. So all over 1 plus y raised to 2 dy. So this is equal to integral from 0 to infinity. Okay, so here y raised to 1 all over 3, I'm going to rewrite it as follows. So what is the number that if you subtract 1 from it, you get this 1 all over 3? I believe the number should be 1 over 3 plus 1, and that is 4 over 3 minus 1. So that should be 4 all over 3 minus 1. And here we have 1 plus y. So what is the number that when you add it to 4 all over 3, you get the power of this 1 plus y here, and that is 2. So I believe the number is 4 over 3 plus 2 over 3. So here we have dy. Okay, so this is clear from this place that this is equal to the beta of 4 over 3 and the beta of 2 all over 3. Okay, wow, this makes very nice sense. So here we have this equal to the beta of 4 over 3 and 2 over 3. Now using the property there, that is the relationship between the gamma function and the beta function. So we have gamma of 4 over 3 times the gamma of 2 over 3 all over the gamma of 4 over 3 plus 2 over 3. And this is equal to, let's see how we're going to evaluate this. So we have here gamma of 4 over 3 times the gamma of 2 over 3 all over, 4 over 3 plus 2 over 3, common denominator, so 6 over 3, and that is 2. So we have here gamma of 2. Okay, now let's see what we're going to do here. Okay, how do we rewrite this? We have here gamma of 4 over 3 here. So remember that 4 over 3 is equal to 1 over 3 plus 1. Okay, so I'm going to write as follows. Instead of writing gamma of 4 over 3, so I will write 1 over 3 plus 1. Then gamma of 2 over 3 all over, gamma of n is equal to n minus 1 factorial. So gamma of 2 will be 2 minus 1 factorial, and that is 1 factorial. Okay, I believe we are proceeding, and this is making sense, right? So now remember the property here. So gamma of n plus 1 is equal to n times gamma of n. So right here we'll be having 1 over 3 times the gamma of 1 over 3. So here we have 1 over 3 times the gamma of 1 over 3, then times gamma of 2 over 3. So 1 factorial is 1. So here we have this equal to 1 over 3 in bracket, here gamma of 1 over 3. So gamma of 1 over 3 times the gamma of 1 minus 1 over 3, because 2 over 3 is 1 minus 1 over 3. So here we have 1 over 3 times, remember the Euler reflection property, so pi all over sine of 1 over 3 times pi, that is pi over 3. So from here now we get this equal to 1 over 3 times pi all over, here we have we have, okay, let's put pi over 1 times, that is 1 over 3 times pi over 1, then times 1 all over sine pi over 3. So this is equal to 1 over 3 times pi over 1 times, what is 1 all over sine pi over 3? Or let's ask ourselves, what is sine pi all over 3? So we get here 1 all over sod 3 all over 2. So, this is pi over 3 times, here, 2 all over sod 3. Okay, so from here, we get our final value, which is 2 pi all over 3 root 3. And this is the right answer to the MIT Integration B problem. Thank you for viewing, and please make sure you share my videos and subscribe to this channel in order to help the channel grow. Thank you so much. See you in our next video.